So guys, we're starting Unit 4 here. Unit 4 is about forces and the laws of motion. We're going to start the unit here. Today we're going to talk about force diagrams and we're going to talk about weight. Our target today is to be able to read and draw force diagrams. After we learn about force diagrams, we'll go ahead and talk about the laws of motion. And then towards the end of the unit, we'll talk about some various forces like friction and other such. So let's go ahead, let's get started talking about force diagrams. Before we really get into force diagrams, let's talk about what forces are for a minute here. A force is kind of like a push or a pull on an object. Forces are measured in a unit called the Newton. Newtons are named after Sir Isaac Newton, who's a kind of a big guy in physics. A Newton is the same thing. Newton is a derived unit. It's the same thing as a kilogram meter per second squared. So kgm/s squared, kilogram meter per second squared. So 1 Newton is the same as 1 kilogram meter per second squared. A Newton is not a whole lot of force. In our imperial system, we usually measure force in pounds. Weight is a force, which is why you're used to measuring your weight in the same unit as we use for force. In the metric system, if you were to talk about your weight, you would technically want to use newtons, even though people throughout most of the world will use kilograms, because they're not really talking about their weight, they're talking about their mass, right? So, weight is measured in newtons. Weight's a force. 1 Newton of force is about 1/4 of a pound. So 1/4 of a pound is 1 Newton, about. So think about a quarter pounder cheeseburger. The weight of that cheeseburger is about 1 Newton of force. So it's not a whole lot of force. We use the symbol F for force. Notice force is a vector. So the F is not italic, it is in boldface because it's a vector. Since force is a vector, sometimes we're going to need to add vectors together for this unit. You remember how to add vectors, right? When we add all the forces acting on an object, we call it the net force. Okay, the net force is just the sum of all the forces that are working on something. So, an object could have multiple forces acting on it. When we add them all together, it's called the net force. And we use a symbol, sigma F. And you might remember sigma notation from algebra. Sigma just means basically add all these things up. So sigma F is the sum of all the forces. It's just all the forces added together. Okay, one particular force that is particularly relevant and is usually acting on most of the objects that we're going to talk about is the weight, otherwise known as the force of gravity. Okay, the force of gravity, the object's weight, we'll use F with a little subscript g to talk about that. Sometimes people use a capital W. So the force of gravity, the weight, could be a capital W or it could be an F with a little subscript g. And it's really very easy to calculate how much force gravity is putting on an object if you know its mass. As long as you're on Earth, then the weight of the object is just the mass times g. So the mass times negative 9.81 meters per second squared. Of course, you're going to get a negative. That's going to tell you, because g is negative, and that's going to tell you that the force of gravity is acting in the downward direction, right? So pretty easy to calculate the force of gravity, the weight of an object. All right, now let's talk about force diagrams for a minute. Okay, a force diagram, it's also called a free body diagram. So, I might say force diagram, I might say free body diagram, they're the same thing. What they are is they're just a little diagram that shows all the forces working on an object, right? So I'll make a little drawing of the object, and then I'll put the vectors for the forces, on the object. And usually the vectors are drawn so that the beginning of the vector is in the center of the object, and they point in the direction that the force is acting, and the length of the arrows, the vector arrows, represents the magnitude of that force, right? So stronger forces will have longer arrows, whereas weaker forces will have shorter arrows. And so, just a little drawing of the object and all the different force vectors working on it. So let's take a look at an example of how to draw one of these force diagrams. Okay, force diagrams are going to be an important tool for us later on. They're going to help us see which forces are acting in the same direction or opposite directions, or which forces might have components working in the same direction or opposite directions. So let's take a look at a little example here about how to draw a force diagram. The example, it says a photograph shows a person pulling a sled. So you see a guy pulling a sled in the picture there. So to draw a free body diagram for the sled, the magnitudes of the forces acting on the sled are 60 newtons by the string, 130 newtons by the earth for gravity, and 90 newtons upward by the ground. Okay, so let's draw a little free body diagram of this here. First thing I'm going to do is I'm going to make a little drawing of the object. I'm going to draw the sled. There's my sled. I don't have to get too fancy with these pictures, right? I mean, that's my sled. Okay, now I can see that we have three forces to deal with. There's the string pulling on the sled, there's the ground pushing up on the sled, and gravity pushing down on the sled. So the string doesn't tell me exactly which direction, but from the picture I can kind of look at it and say it's kind of like this direction. Okay, it says that is 60 newtons. So I'm going to make my arrow maybe about that long, and about that long represents 60 newtons of force. Okay. The second force it tells me about is the force of gravity, which should be pointing down, right? And that is 130 newtons. 130 is a little bit more than twice as much as 60, so I'm going to make my arrow approximately maybe twice as long. That's 130 newtons. Okay. And notice my force vectors start from the center of the object there. And then the third force is the ground pushing back up on the sled, and it says that's 90 newtons. So 90 is going to be a little bit longer than this, so maybe something like that. 90 newtons. And there is my force diagram. Pretty simple. Okay, one other example here. This one says a book rests on a desk. Gravity applies a downward force to the book, and the desk pushes up on the book with an equal force. So draw a free body diagram of the book. Okay, so first thing, of course, I'm going to draw a book. And I'm not going to get too fancy here. A book. Okay, and it says gravity applies a downward force. It doesn't tell me how much, so I'm just going to draw an arrow down. And that's the force of gravity. So maybe I'll label it FG. Or since that's the weight, you could label it with a capital W or something. And then it says that the table, I think it was, pushes back up on the book with an equal force. So that's going to go up, and it's going to be about the same length as this one, right? So, and that is the other force. And there's my free body diagram. Pretty simple. Okay, so there's a little bit about forces, about weight, and about free body diagrams, or otherwise known as force diagrams. Hopefully that helps us be able to read and draw force diagrams. So until next time, take it easy.